The last time I saw you, we were talking about limits, evaluating limits algebraically, and we were discussing the indeterminate forms and some techniques that we can use to evaluate a limit when we first get an indeterminate form after substitution. We talked about factoring and reducing last time, and today we're going to go on to another technique if you cannot factor. One technique is simplifying a complex fraction. So if your function is a complex fraction, simplify it, and then you can find the whole. So right now, if we just plug in -5 for x, if I put in -5 for x, I get a -1 plus 1, which would be a 0. I don't want to put it right here, but I might put it over here. We get a 0 on top, and if I put -5 in the bottom, I get a 0 on the bottom. That's indeterminate. So we need to manipulate this function so that we can locate our whole and cancel out our whole. We still know that there's a whole though. This tells me there's a whole. It's just really hidden. It's hiding. We have to find it. So simplifying a complex fraction will allow us to find that whole. So when I see this, I look at what is making this a complex fraction, and that x right there is making this a complex fraction. I multiply top and bottom by that x to get rid of it. And when I do that, remember that we keep writing limit until we can plug in successfully. We keep writing limit. So 5 over x times x, the x's will cancel, you're left with the 5. 1 times x is x, so don't forget to distribute that. This is going to be a plus x, so 5 plus x. Now on the bottom, only distribute where you had a denominator. Don't do it elsewhere. So don't distribute this x through. If you do, you're losing the factor that makes your whole. I see it right there. I don't want to distribute or you're going to lose it. So leave it written like this. 5 plus x times x, right there. So I see my whole now. There's the whole right there. We can reduce it, and it leaves a 1 on top and an x on the bottom. So put -5 into the remaining x after those cancel, and we're left with 1 over -5, which on a multiple choice answer they would call it -1/5. Alright, let's go to this one. Here we have, we're letting x go to 2, so if I just substitute, I'm going to have 1/2 minus 1/2, which is 0, and then I have 2 minus 2, which is 0, indeterminate, and there's a whole. I just need to find it. It's hidden, right? So we're going to find the whole. I'm going to multiply top and bottom by something that's going to get rid of my complex fraction. There are two things making this a complex fraction, this x and this 2. So I'm going to multiply both top and bottom by 2x. Top and bottom by 2x. Since I'm multiplying by 1, I'm not changing the value of this expression. Okay? So I have limit as x goes to 2. Okay, distribute this 2x to each term in the numerator, but don't distribute it in the denominator because nothing's going to cancel. Just leave it split up, okay? So 2x times 1 over x, the x's will cancel. I'm left with 2 times the 1, which is just 2. Next term, we have the minus. Keep your minus. The 2's cancel, and we're left with 1 times x, which is just x. On the bottom, I do not multiply. I just leave it split up. Okay. Did we find our whole? Kind of. Kind of. These are not exactly the same, but they do reduce, right? They do reduce. What do they reduce to, though? They don't reduce to a 1 because they're not identical. They don't reduce to a 1. If we factored out a -1, then they would be identical. So this reduces to a -1. Put the 2 into the remaining x, and we have -1 over 4, or -1/4. Number C, part C. Okay, if I put 3 in for x, I'm going to have 5 over 5, which is 1, over 4 minus 4 over 4, which is also 1, that's 0, right? On the bottom we have also a 0. So an indeterminate form, there's a hole somewhere, we just need to find it, cancel it out. So what are we going to multiply top and bottom by this time? Well, whatever's making the fraction complex. So x plus 2 and x plus 1. Oops. Sorry. Goodness. Okay, like that. All right. I'm going to rewrite my limit here. Okay, up on top. The x plus 2's cancel. I'm left with 5 times x plus 1. Minus the 4 times the x plus 1's cancel. I'm left with the 4 times the x plus 2. On the bottom, do not multiply out. Leave it factored. If you multiply it out, you're just going to have to factor again, and it won't be as easy to factor as it was to multiply it out. Okay? So, let's simplify up on top because that hole's still hidden. Distribute your 5. Distribute your -4. Leave the bottom factored. Okay, 5x minus 4x is x. 5 minus 8 is a -3. And we found the hole. X minus 3 and x minus 3. X minus 3 on top and bottom. There's our hole. They reduce to 1. Put 3 into the remaining x's, and we get 1 over 5 times 4, which is 1 over 20. So that limit reduced to 1 over 20. Okay? Another example, similar. At this point, I would probably in class let you guys try one. So if you want to try this and then come back on your video, that would be great. Alright, plug 1 in for x, and we get 2 over 2, which is 1, minus 3 over 3, which is also 1, so we get 0 over 0. That's indeterminate, and there's a hole. Got to find the hole. We're going to multiply by x plus 1, x plus 2, divided by x plus 1, x plus 2. Alrighty, rewrite your limit. Okay, first term, the x plus 1's cancel. We're left with 2 times x plus 2. Minus the x plus 2's cancel. We're left with 3 times x plus 1. All divided by x minus 1, x plus 1, x plus 2. Don't multiply that out. Just leave it factored. Distribute your numerator. We'll have a 2x plus a 4 minus 3x minus 3. Keep rewriting your denominator. Keep rewriting your limit until you can plug in. Until you cancel your whole, keep rewriting your limit. Okay? Alright, let's see. 2x minus 3x is a negative x, right? 4 minus 3 is a 1, so this is a 1 minus x on top. Did we find our whole? Yes, we did, but it doesn't cancel to a 1, does it? It cancels to a -1, so be careful with that. Now that we cancel these, we're going to plug in x1 in for x for our remaining x's. We'll have a negative 1 over 2 times 3, so negative 1/6. Alrighty. E. Alright. So let's see. Plug 5 in for x. 10 over 10 is 1 minus 1. We're going to get 0 over 0. I'm not even going to write down 0 over 0. I know that there's a hole. I know what I need to do here. I see a complex fraction. I know how to handle a complex fraction, right? Okay, so in class I would ask, what do we need to multiply top and bottom by? So what do we need to multiply top and bottom by here? Well, I have a 2x there and an x here. Do I need to multiply by 2x times x? I will tell you that it won't hurt to do that, but you really only have to multiply by 2x because that's going to cancel out the 2x here and the x here. So it's okay if you want to multiply by 2x times x over 2x times x, but you're going to have an extra x involved, and that's okay. Not going to hurt too badly. Rewrite our limit. Here the 2x's cancel, left with just the 10. Minus, here the x's cancel, I'm left with 2 times 5, which is 10. And on the bottom we have this. How does that reduce? That reduces to 0. 0 over anything is 0, right? So it reduces to 0. That means when it reduces, it's gone. It's just a 0. The limit as x approaches 5 of 0 is just 0. I could show you this on the calculator and you would see that the graph is indeed going to 0. There's a hole there, but it is going to 0. Okay? It is going to 0. So that's what happened there. One more of these. Okay? So if I just let x go to 2, we're going to have 0 on top. We're going to have 4 over 4 minus 7 over 7. So that's 0 on the bottom. I know there's a hole. It's a complex fraction. I know what to do. I'm going to multiply by top and bottom by everything that makes this a complex fraction. So I'm multiplying by x plus 2 times 9 minus x. This time it's on the bottom that I'm getting rid of, but that's okay. We'll handle it the same way, just all of our business is on the bottom. Up on top, I'm not going to multiply it out. I'm just going to leave it factored. We want it factored. Okay, on the bottom, the x plus 2's cancel. I'm left with 4 times 9 minus x. Minus 7 times, okay, the 9 minus x's cancel. I'm left with 7 times that x plus 2. Time to simplify that denominator. I'm leaving the numerator alone. We have a 36 minus 4x minus 7x minus 14. Got some bigger numbers this time, but nothing we can't handle. Okay. 36 minus 14 is 22. Negative 4x minus 7x is negative 11x. Okay, where's our hole? Well, we don't know yet. We can factor out an 11 though, can't we? So take out an 11 and we're left with 2 minus x. Okay, did we find our hole? We sure did. We found our hole. Okay. They're not identical though. We're going to factor out a negative 1. They reduce to a negative 1. And now we plug in our 2 for the remaining x's, and we'll have 4 times 7 divided by negative 11. So this is a negative 28 over 11. An interesting limit that time. Okay, so we do manipulate things like this in calculus quite often for various reasons. Okay, one more algebraic technique, and that is, I'm not sure if in class I might just make this another day and let you guys do some examples for homework from that worksheet. But I think for the notes, for the video notes, I'm going to go ahead and make this keep going. We've only been on here for 15 minutes, so I think we're okay. All right. If it's not complex, and if you don't see a way to factor, so here if I put in 16 for x, I'm going to get 0 over 0. So I know there's a hole. I know there's a hole, but it is really hidden. This is not a complex fraction. I don't know how to factor it, so we have to do something else. And when you don't know what to do, try to multiply by a conjugate. When I see a square root, I think conjugate, multiplied by a conjugate. Okay? So I'm going to multiply top and bottom by the conjugate wherever the square root is. So the square root is up here. The conjugate of that is the square root of x plus 4. So I'm multiplying by square root of x plus 4 over itself. Okay, rewrite our limit. Multiply where your conjugates are, multiply. Do not multiply where your conjugates are not. So only multiply where your conjugates are. So square root of x times square root of x is x. The middle term here will cancel out. So this is a 4 square root of x minus 4 square root of x. They cancel each other out, which is exactly why we multiply by a conjugate, right? So they cancel each other out, and then our last term will be a negative 16. On the bottom, we have x minus 16, which is why we do not multiply out the bottom. Okay? We found our hole, x minus 16 over x minus 16. They're identical. They cancel to, they reduce just to a 1. Plug in 16 for our remaining x. We have the square root of 16 plus 4, which is, the limit will be 1 over 8. Okay? The numerator, when we just substitute in 5, the numerator is 0. The denominator is the square root of 4, which is 2, minus 2, that's 0. Got 0 over 0. I know there's a hole. Gotta find it. Can't factor it. It's not a complex fraction. So what do? We multiply by a conjugate. I go to where my square root is, and I'm going to multiply by the conjugate of that, so x minus 1 plus 2 over the square root of x minus 1 plus 2. Okay? I'm not going to multiply where my conjugates are not. So I'm leaving my numerator, in this case, alone. I am multiplying on the where my conjugates are, though. So square root of x minus 1 times square root of x minus 1 is x minus 1. The middle term zeroes out. I'm left with negative 2 times 2, which is a minus 4. And we get, on top, 5 minus x times square root of x minus 1 plus 2 divided by x minus 5. We found our hole. They're almost identical, but they reduce to a negative 1. Right? Plug 5 into your remaining x. You're going to have the square root of 4 plus 2 over negative 1. That is 2 plus 2 over negative 1, 4 over negative 1. This is negative 4. Okay? Next one. All right. if I plug 0 in for x, cosine of 0 is 1. 1 minus 1 is 0. Sine of 0 is 0. There's a hole here. It's really hidden. We don't know where it is. There's no square roots. We can't factor this. There's no complex fraction. This is one where it's like, what do you do? Well, the only thing we can do is multiply by a conjugate. What conjugate? Well, the only conjugate that I can see is up in the numerator because that's the only thing that we have two terms in. So a really hidden one, but that's what we have to do here. I'm going to multiply top and bottom by the conjugate of cosine x minus 1, which is cosine x plus 1, over itself. And again, where my conjugates are, I'm going to actually multiply it out. Where my conjugates are not, I'm going to leave it alone. So on the bottom, I'm just going to leave it sine x times cosine x plus 1. Okay? Up on top, we have cosine squared x, or you can think of that as cosine of x all squared, but we write that as cosine squared x. The middle term zeroes out, as all conjugates do when you multiply them. And then we have a minus 1. All right. Now what? Well, I see that cosine squared x and a minus 1. So I'm thinking of our Pythagorean trig identity that says sine squared x plus cosine squared x is equal to 1. I have cosine squared x minus 1. There's my cosine squared x, there's my 1. If I subtract the 1 over to be with cosine squared, I'll move the sine squared over and it will be negative. So this is negative sine squared x because of the trig identity. So that is, I might go ahead and rewrite that for you. That is negative sine squared x over sine x times cosine x, and we found our hole. It was a sine x. So I'm going to reduce 1 sine x. It'll leave a sine x on top, a negative sine x on top, and cosine x plus 1 in the denominator. Plug 0 in for what remains. What is sine of 0? Sine of 0 is 0. Negative 0 is still 0. 1 plus 1 is 2. 0 over 2 is 0. So in every one of these like this, you're going to use that Pythagorean trig identity. Let's do another one. Let's see what happens over here. So when we first plug 0 in for x, we have 0 over 1 minus cosine of 0 is 1, so we have 0 over 0 again. So I'm going to multiply top and bottom by the conjugate. 1 plus cosine x over 1 plus cosine x. Keep writing our limit. Okay, only multiply where your conjugates are. Up on top we have sine x times 1 plus cosine x. On the bottom we're going to have 1 times 1 is 1. The middle term zeroes out. We have a negative cosine squared x. Okay, so what is 1 minus cosine squared x? Sine squared x plus cosine squared x is 1. We have a 1 minus cosine squared x. So how do I get that? Well, I get that by moving this cosine squared over here, and I'll be left with a sine squared x. So sine squared x will be 1 minus cosine squared x. So in place of this, I'm putting a plain sine squared x, not a negative this time. So one of these signs will cancel. and I'll be left with 1 plus cosine x on top and a single sine x on the bottom. Now we're going to let x go to 0 again. We're going to have a 2 on top. The top is going to 2. I'm not going to put an equal to sign because I see what's happening down here. The top is going to 2 because cosine of 0 is 1. The top is going to 2. The bottom is going to 0. The bottom is going to 0. And you may or may not remember what happens when we're going to 0 on the bottom. Because this can be positive or negative and we don't know, it's not a one-sided limit, we don't know what sign it is, we cannot say that this is infinity or negative infinity. It's one of them, we just don't know which. We need to know which side it's coming from to be able to designate either positive or negative infinity. So since we don't know, we write DNE. Does not exist. 0 on the bottom does not exist. Okay, so next up, put 0 in for x. Square root of 2 minus square root of 2 over 0. Definitely a hole somewhere going on. I'm going to multiply both sides by a conjugate. The conjugate, you only change that sign. Rewrite our limit. Okay. Where your conjugates are, you multiply. So square root of x plus 2 times square root of x plus 2 is x plus 2. The middle term zeroes out. And we have negative square root of 2 times positive square root of 2. That is a negative 2 over x times all of this. Okay. Up on top, we just have an x, right? Because we have 2 minus 2. That's 0. We have x over x, and those x's will cancel. So that all cancels with that x, leaving a 1 on top. Plug 0 into what remains for your remaining x's. You have 1 over square root of 2 plus square root of 2, which is 1 over 2 square root of 2. And for calculus, we can just leave it like that. We could rationalize it, but rationalizing is not going to simplify this one. We would just get 2 times 2 down there, which is 4, which is more simple. Oh, yeah, both are good. Both are fine. Know how to get to this one, but chances are in a multiple choice answer, that would just be your answer. Okay, one last one. It's another one with the sine and cosine. So if we put pi over 2 in for x, sine of pi over 2 is 1, right? Sine of pi over 2 is 1. 1 minus 1 is 0. Cosine of pi over 2 is 0. We get 0 over 0. We're going to multiply by the conjugate of 1 minus sine x. Rewrite our limit. Distribute up here, so FOIL this out. 1 times 1 is 1, the middle term zeroes out, minus sine squared of x. On the bottom, do not multiply. You're going to lose your whole if you do. We have 1 minus sine squared x. Well, sine squared x plus cosine squared x is 1. I want 1 minus sine squared x, so I'm going to move the sine squared x to the right, where it's going to be a minus 1 minus sine squared x. I'm left with cosine squared x. So this right here is cosine squared x. One of these cosines reduce, and I'm left with the limit as x goes to pi over 2 of cosine x over 1 plus sine x. Plug pi over 2 into what remains. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so in the denominator we have a 2. This whole thing is 0, and we're done. So these are the techniques for evaluating a limit when you get for all limits, but the first one is your go-to. You always do that first. Then, if you get an indeterminate form, you do one of these.